remind this. Inner product spaces, orthogonalization, etc. Okay, etc. From 115a. Okay. All right. So let's remember where we stopped last time. So we have defined inner product spaces, well, or recalled the definition of inner product spaces and some of the basic properties. And given an inner product space, okay, so recall definition, if V is an inner product space and X is an element of V, a vector in V, okay, then the norm denoted like this, the norm of the vector X is simply the square root of the inner product of X with itself, okay? So that's the definition of the norm associated to a given inner product space. Note in particular that here we're taking a root of a certain scalar, right? So in particular, we need to know for this definition to make sense that in the field of scalars F of V, every element has a root, or every element that can appear as an inner product has a root. So this is true both in the real numbers and in the complex numbers. In the real numbers, this makes sense because this is positive, right? Or non-negative more precisely. And we know that non-negative elements have square roots in the real numbers, right? Okay, so let's consider an example which motivates this definition, in fact. So this is an example of the usual Euclidean distance. So assume we have V, the vector space Rn for some n, with the standard inner product. Okay, so remember the standard inner product is just the same as the dot product given by the same formula, the dot product. So now if I have X vector with the coordinates a1 through an, yeah, then the norm of X with respect to the standard inner product is going to be the norm of a1 through an. Okay, so I just write the coordinates for the vector X, and this is calculated as the square root of the inner product of A with itself. Now the inner product with itself we get by the formula I equals 1 through n ai square, right? And then we have to take it to the power 1/2. Okay, and this is of course the usual Euclidean distance or Euclidean length of the vector. Euclidean length of a vector, right? Like if I have a vector like this, let's say this is X, so to calculate its length, we look at the X coordinate, right? This is a1, we look at the, so this is the case R square. This is a2, and this is the length is given by the square root of the square of a1 plus the square of a2. Yeah. All right. So this is a standard example, but our definition makes sense in any inner product space, so it's more general. Then we have the following theorem, 6.2 from 115a, which gives us some of the basic properties of the norm. So let V be an inner product space, okay, over some field of scalars F. So remember, throughout this discussion here, we're assuming that F is either the real numbers or the complex numbers, okay? Then for all xy vectors in V and C, a scalar in F, we have the following properties. So first, the length of the norm of C, of the vector X multiplied by C is just the norm of C, the norm of X multiplied by the absolute value of C, right? So when we are scaling by C, we just it corresponds to multiplying the length, as you would expect from even the name scaling suggests, right? That the length changes by multiplying by c. Question: why won't this work over ZP, for example? Yeah, so good question. I think I mentioned something briefly last time, and I'm going. I should still send it to all of you. Like, why do we care that the field is the real, so the complex numbers? So there are several things here. You want to have square roots first of all, like I remarked. So to be able to even talk about the norm, right? We need to be able to take square roots of everything. And there are some other factors for the theory to work out smoothly. Like we want the elements of the field to have absolute values which behave naturally, etc. So many things would work over more general fields. Okay, but I'll send you a link about this. There's something called Euclidean fields is a relevant notion here. But this takes us a bit off topic. Yeah, maybe we can discuss more in the office hours if you want later. So, okay, sure, yeah. All right, so let's continue. So I just recall some of the basic properties of norms. So we have the norm of the vector x is 0, if and only if the vector itself is 0, okay? So, and we always have that the norm is non-negative. So for any vector, the norm is non-negative. Again, of course, you would expect it from any reasonable notion of length, right? Like the negative length is not meaningful. All right. So now we have the very important Cauchy-Schwarz inequality. So this is probably the most important inequality in mathematics. Yeah. So in the vector form, so in our situation, this corresponds to the following. If I take the inner product of two vectors, x and y, then the absolute value of the inner product is bounded from above by the norm of x times the norm of y. So we have this relationship between the norms of two vectors and the absolute value of their inner product. Okay, this is Cauchy-Schwarz. And D, the other extremely important inequality, is the triangle inequality, which tells us that the distance, well, okay, let me state it for norms, yeah. But the usual triangle inequality that if you want to go from x to y and from y to z, then this is going to take longer than just going from x to z directly. Rephrased in terms of the norms, this corresponds to saying that the norm of the vector x plus y is less or equal than the norm of x, than the norm, too many lines, than the norm of x plus the norm of y, right? So we have this triangle inequality for the norms. All right. So these are some of the key properties of the norm in an arbitrary inner product space. And now, once we are equipped with norm, we can and inner product. We can talk about angles between vectors. Yeah. Or at the very least, we're able to define orthogonality for vectors. And we also can talk about the length of the vectors. So this allows us to make the following definition for this special kinds of relationships. Yeah. So let V be an inner product space. All right. So then we say that two vectors x, y in V are orthogonal if the inner product of x and y is equal to 0. Okay. And if you think about the usual dot product, then you see orthogonality corresponds exactly to the usual meaning of orthogonality, that two vectors at an angle 90 degrees on the plane, for example. Yeah. Okay, so that is one. Now two, we can also talk about orthogonality for a set of vectors. So a set S of vectors in V is said to be orthogonal if any two distinct vectors in S are orthogonal. Okay. So here we say distinct, of course, right? Because And any non-zero vector cannot be orthogonal to itself, because remember the inner product is positive unless x is 0, of x with itself, I mean. Yeah. Okay, so we have this. Now we can also talk about vectors of unit length. So a vector x in V is said to be a unit vector if we have that the norm of x is 1. Okay. And finally, a set S of vectors is orthonormal. Okay, so it's like orthogonal, but orthonormal. If S is both orthogonal, so S is orthogonal in the sense of definition 2 here, yeah. And every vector in S is a unit vector. Okay. And note that every vector can be normalized, of course. So for any x, an element of V, we know that if I look at 1 over the norm of x, okay, as long as x is non-zero, so let's say here x non-zero, 1 over the norm of x times x is a unit vector. Right? So we just scale down by the norm. So the norm is going to be 1 by the basic property, right? Because remember, multiplying by scalar corresponds to multiplying the norm by the absolute value of the same scalar. Okay. All right. So now, having defined these properties, we're interested in orthonormal bases. So this is somehow the nicest kind of basis that we can find in an inner product space. Let V be an inner product space. Okay. Then a subset of V is an orthonormal basis. Well, if it is both orthonormal and an ordered basis, yeah. If it is an ordered basis, that is orthonormal. Okay, so it consists of all vectors of length 1, unit vectors, and they are all pairwise orthogonal. All right, so example, if you look at the standard basis, for the inner product space, Fn, so we think about it as with the standard inner product. Okay, is orthonormal. Right, because each vector in the standard basis is a unit vector. It just has 1 in one of the coordinates and zeros everywhere else. So its norm with respect to the dot product is going to be 1, yeah, and they're all orthogonal, which is easy to see. All right, and we know that the standard basis is nice to work with, right? So the idea now is to have bases in a general inner product spaces, which behave as nicely in this respect as the standard basis in this vector space of N. So we're interested in finding orthonormal bases. And for this, there's a general method, the so-called Gram-Schmidt orthogonalization. Okay, so let me recall some of the results about it. So first of all, there was a theorem SIG3, which tells us how to determine the coordinates with respect to an orthogonal subset. Okay, so namely assume V is an inner product space. Okay, and assume that S is a set of vectors V1 through Vk in V. So assume this is an orthogonal subset of V, so that all of these vectors are non-zero. So vi is not equal to 0. Okay. Now assume that y is some vector in the span of S. Okay. Then we can write y. So we know we can write y as a linear combination of the vi, right? Because it's in the span. But moreover, because of orthogonality, we actually have an explicit formula to calculate the coordinates of this vector with respect to the vi's. So we have that y is given by the sum I from 1 over k. And now for the coordinates, we have the following expression. So we take the inner product of y with vi and divide it by the square of the norm. So take norm of vi square times vi. Okay, so note here, this is a scalar in F, and this is the corresponding coordinate of the vector y. So it's given by this explicit formula in terms of the inner products. Okay, so this theorem has a couple of corollaries. The first one, if in addition the set S is in fact orthonormal, yeah, so now we assume in addition that all vectors in it are unit vectors, and y is in the span of S, then the formula becomes simpler, right? Because then we can write y as the sum over I from 1 to k, the inner product y with vi times vi, right? So note we don't no longer have to divide by the square of the norm because the norm is 1. Yeah, so the square of the norm is 1 as well. So in this case, the formula becomes even simpler. Okay, this is corollary 1 and corollary 2. We have that if V is an inner product space and S is a subset of V, orthogonal, then V is not equal to 0 for all V in S. Okay, so assume it consists of non-zero vectors. Then we have that S is linearly independent. All right. So we have this implication. Orthogonality of a set implies linear independence. And this again, why this is a corollary, you can see it quickly from this expression, right? From this formula. Because if all the vectors are orthogonal, if you try to express one of them, for example, Vj, using this formula, you see that we get the inner product of Vj with Vi here, right? But all of those are going to be 0 if the vectors in the set are orthogonal, right? So we're going to get that there are no non-trivial linear combinations. Basically, that's the point. Yeah. So it's corollary 2. Just an idea why it follows from the theorem. All right. So we see, hopefully, these observations tell us that orthonormal bases would be useful, right? Because they're easier to work with than just arbitrary bases, because we have these extra formulas. So the next point is that we actually should be able to find them. And this is theorem 6.4 from 115a. This is what the so-called Gram-Schmidt orthogonalization process. Yeah? So a very important result, which tells us that it's always possible to find an orthogonal or even orthonormal basis. Okay, so Gram-Schmidt orthogonalization. Okay, some long words, but anyway, Gram-Schmidt. Yeah. So assume V is an inner product space, and we have S, a set of vectors, which we denote as W1, Wn. So it's a set of vectors in V, and assume that they're linearly independent. Okay. So we start with a linearly independent set of vectors. Then we let S prime be the set V1 through Vn, where the first vector V1 is simply W1, and the vector Vk in this list is defined recursively as follows. Okay, so we have a formula. So we take Vk to be Wk minus the sum over all j from 1 to k minus 1. Okay, and this is going to be a linear combination of the vectors Vj, the previous vectors, the previously constructed vectors. So we already know what Vj is, right? We are arguing by recursion on the index of the vector. And the coordinates are going to be given as follows. So we look at the inner product of Wk with Vj, and we divide it by the square of the norm Vj square. Okay. So we define it like this for all k between 2 and n. Okay. So you see this is a recursive formula. It allows us to define the vector Vk in terms of the previously constructed vectors. So in terms of Vj for j smaller than k, and the Wk, of course. Okay. All right. So this gives us a way to define a new set of vectors, Vi, from Wi. And then the theorem says that this new set, S prime, is an orthogonal set of non-zero vectors. Okay. And moreover, the span doesn't change. So the span of S prime is the same as the span of S. All right. Okay, so this is the Gram-Schmidt. Given a set of linearly independent vectors, we can modify it to produce a set of orthogonal vectors without changing the span of this set. Okay, so now using this theorem, as you remember, we can obtain some nice results. In particular, we can find orthonormal bases. So that was kind of the main motivation for this theorem, theorem 6.5. So assume V is a non-trivial vector space, moreover with an inner product. So an inner product space, finite dimensional. Yeah. All right. Then V has an orthonormal basis beta consisting of some vectors V1 through Vn. Okay, and why? How does it follow from the previous theorem? Well, you just start with a basis for V, right? Then we apply Gram-Schmidt to get an orthogonal set of vectors. Let me see a question in the chat. Do you need to normalize? Not at this stage. I mean, look, the point of Gram-Schmidt is just to produce a set of orthogonal vectors, starting with a given set of linearly independent vectors. But then, of course, we can normalize them. So that's what I'm doing here in this theorem. So first, I start with the basis for V. Then I produce an orthogonal set of vectors, which have the same span. So they still span the whole space, right? And they are linearly independent, because we just remarked that orthogonal non-zero implies linearly independent. Okay, but then of course we can normalize them if we want. Normalization is easy. You can always do it after the fact, right? Once you have orthogonal vectors, then you can divide each of them by the norm. Well, multiply by 1 over the norm. And that doesn't change the span either, right? They remain linearly independent and the span doesn't change. Okay. So, all right. So we can always find the basis like this, thanks to Gram-Schmidt. And then if we have an orthonormal basis, we have that for any vector x and v, its coordinates have this special presentation. So we have that the coordinates are given by the inner products. Okay. So the coordinates of this vector are all of the form x inner product with vi. All right. Excuse me. So this is theorem 6.5. Let's record a couple. Let's record the corollary first of all. So we have a statement for matrices, for matrix representations. So since we have coordinates in this simple form here, it allows us to write matrix representation also directly, right? So assume V is an inner product space of finite dimension, okay? And assume that beta given by V1 through Vn is an orthonormal basis, right? Now assume I'm, excuse me, assume I'm also given a linear operator. So I have T, a linear operator on V, and assume that we take, excuse me, we take the matrix representing T with respect to the basis B. Let it be A, okay? Let's denote this matrix by A. Then the coordinates of this matrix are easy to describe. So then for any ij, we have that aij is simply the inner product T Vj with Vi, right? So this is just by applying the previous theorem, because we have this simple form for the coordinates. So just if you just try to write out the matrix representing it, you see that the entries of the matrix are of this form. All right. Okay, so this is concerning existence of orthonormal bases. Next, let's talk about orthogonal complements. So this is a related important notion, definition, a special kind of subspaces. So assume we have S, a subset of V, which we assume to be non-empty also, okay? And assume that where V is an inner product space, all right? We define as perp, this is a perpendicularity symbol, yeah, called as perp, to be the set of all vectors X and V, for which we have that the inner product of X with Y is equal to 0 for all Y in S, okay? So in other words, we look at the collection of all vectors X, which are orthogonal to all vectors in S, right? So we look at all vectors X and V, which are orthogonal to all vectors in S simultaneously. This is the set we denote as perp, and we call this set the orthogonal complement of S. The orthogonal complement of S. Okay. All right. So now, what are the properties of this set? So note first of all that this is always a subspace. So S perp is a subspace of V for any set S, okay? So S can be an arbitrary set. The orthogonal complement is always going to be a subspace. This is easy to check as usual, so you can check yourself, just checking that it's closed under addition and multiplication by scalars, yeah? This follows from the properties of the inner product. So we have that this is a subspace. Moreover, we have that the orthogonal complement of the trivial subspace, the zero subspace, is all of V, and conversely, the orthogonal complement of all of V is just 0. Okay. All right. So we have these basic properties, and now we have theorem 6.6, which tells us how to decompose a vector into two components. One which is in a given subspace and one which is in its orthogonal complement, okay? So this was theorem 6.6 in the course in 115a. So assume W is a subspace of an inner product space V, okay? And assume that the dimension of W is finite. Let Y be a vector in V, okay? Then there exist unique vectors U in W and Z in the orthogonal complement of W, such that y can be written as the sum of the two. So y can be written as u plus z. Okay. Moreover, we know how to calculate this u. So if, let's say, v1 through vk is an orthonormal basis, for this subspace W, then we can write U as follows. So U is given by the coordinates I from 1 to k, y inner product with vi times vi. Okay, so we have this formula for U, the component which is in W, and then Z is the corresponding component in the orthogonal complement. All right. If you want to draw a picture here, right? So this is the usual situation. Like I have, for example, in R2, let's say W is just the x-axis. Let's say this is W, and assume I have some vector. What did we call it here? Y. Yeah. So assume this is Y, some vector in V. Then it can be written as the sum of two vectors. Namely, the first one is going to be U. Okay, so this is U. So U is a vector in W. And we have the orthogonal complement vector Z. Okay, so the sum is Y. So this theorem just abstracts from this simple picture. All right. Okay. So given this idea that we can split a vector like this, we can talk about the orthogonal projection of a vector onto a given subspace. So let's make this definition precise. So this vector U, which we just described, so the vector U in the theorem is called the orthogonal projection of Y on the subspace W. Okay. And so corollary of this theorem also is that we can describe U using the norm. Okay. So U is the unique vector in the subspace W that is closest, and I put it in the quotation marks, to Y. Okay. So what do we mean by the closest here? Well, we mean that the norm of the distance is smaller, is as small as possible. So namely, we have that for any other vector x in W, okay, the norm of y minus x, which remember we think about as the distance between y and x. So this is greater or equal than the distance between y and u. Okay. And moreover, this is an equality if and only if x is equal to u. So the orthogonal projection of a vector onto a subspace is the unique vector in that subspace that is as close to y as possible among all vectors in the subspace. Let me see, there's a question in the chat. So then whenever W is a subspace, V equals direct sum. Oh, okay, yeah. That's what I'm going to say next. Yeah, so, but yes, you're right. So in particular, we can deduce theorem 6.7. Well, this was in 115a again, which connects this to perp and the direct sum. Yeah. So suppose we have S consisting of vectors v1 through vn. So assume this is an orthonormal set. Okay. Orthonormal set in an n-dimensional inner product space V. Okay, so assume I'm given such a set, orthonormal set. Then we have the following claims. So way S can be extended to an orthonormal basis so we have V1 through Vk. This is what we were already given, and it can be extended to Vk plus 1 through Vn, an orthonormal basis for V. Okay, so this is like a familiar property. Remember, we know this already for just for vector spaces, that any linearly independent set can be extended to a basis. Okay, this is an elaboration on the same fact, but now in an inner product space. So if we have an orthonormal basis, if we have an orthonormal set, we know that in particular it's linearly independent, right? Remember, orthogonality implies linear independence. So if we're given an orthonormal set, we can extend it to an orthonormal basis for the whole space. Question, should S be V1 to Vk? Oh, yes, thank you very much. Yes, this should be Vk, right? So yes, I'm saying I'm given some number of vectors, V1 through Vk, in a inner product space of possibly larger dimension M, let's say. So yeah, thanks for, this is important. So what we are saying is that it can always be extended. This is A, okay? Now part B, if we have that W denotes the span of the set S, then we can write S1 to be the set consisting of all these other vectors. So we have Vk plus 1 through Vn, okay? So these are the vectors in the orthonormal basis, which we had to add. And then this is an orthonormal basis for the orthogonal complement, so for W perp, okay? So we get this, and now what Amar already said earlier, so it follows from these two that we can write the whole space as the direct sum, okay? So we can deduce from A and B that if W is any subspace of V, okay, then first of all we have that the dimension of V is equal to the dimension of W plus the dimension of W perp, right? So this just follows because this is a basis for the orthogonal complement, right? And S is given by this. So we have this, and we conclude that V is in fact the direct sum of W and its orthogonal complement. So given any subspace, finite dimensional subspace, the whole space splits into direct sum of this subspace and its orthogonal complement. All right. So we have these properties of orthogonality. All right. And the last thing I want to review from 115a is the adjoint of a linear operator. All right. So I'm okay. Let me stay here for a minute, maybe. And if there are any questions, please go ahead and ask. Okay, let's see. If V isn't finite dimensional, is it still the sum of a subspace and its orthogonal complement? Yeah. So we want to assume finite dimensionality throughout. Okay. These things become a bit more subtle in the infinite dimensional situation. So so we focus on finite dimensional case here. All right. So let's move on. So the last thing we need from 115a is the adjoint of a linear operator. Okay, so an important notion. So it's a way to associate a new operator to a given linear operator. Okay, so how? So assume, okay, first of all, the setup is the same as before. So let V be an inner product space and assume that Y is a vector in V. All right. Then we can consider a certain linear function. So namely, we can look at the function G, which goes from V to F, defined by saying that G of X is equal to the inner product of X with Y. Okay. So it's a function which takes a vector X and sends it to the inner product of X with Y. So we assume that Y is fixed. Okay. All right. So first of all, this function is linear. Why is it linear? Well, by the properties of the inner product. Because remember, the inner product is bilinear. So it's linear in each coordinate. Well, in the coordinate on the right, it's linear up to taking complex conjugate in general. Okay. So anyway, here we are multiplying on the left. So this is a linear function. And there is a converse to this claim, which says that every linear function in a finite dimensional inner product space is of this form, in fact. So this was theorem 6.8. Okay. So linear. Conversely, we have this theorem 6.8. So which tells us that if V is an inner product space over some field of scalars F, so either the reals or the complex numbers, and the dimension of V is finite, okay, then assume I'm given any linear transformation G from V to F, okay, be any linear transformation. Well, linear transformation or linear linear functional, yeah, as we call it sometimes also. So assume I'm given any G like this, then it has to be of the form described above, in the sense that there exists a unique vector Y in V such that G of X is given by the inner product of X with Y for all X in V. Okay, so no matter what function, what linear function from V to F you take, it's already represented by the inner product with some fixed vector Y. So this Y depends on G, right? So this Y depends, of course, on G. Okay, so we have this converse result, okay? And this leads to theorem 6.9, which tells us how to define the adjoint operator. So assume V is a finite dimensional inner product space and assume that T is a linear operator on V. Okay, then there exists a unique function T star from V to V such that we have the following relation. So we have that the inner product of T of X with Y is equal to the inner product of X with T star of Y. And this holds for all X, Y in V. Okay. Moreover, in this case, this unique function T star has to be linear. Okay. So once again, if I'm given any linear operator T like this on a finite dimensional inner product space, then I can find another linear operator T star, which is connected to T via this funny formula. So if I calculate T of X inner product Y, this is the same as X inner product T star of Y. And this holds for all X and Y in V. okay? And this function T star, or this linear operator T star, is called the adjoint of T. So definition, the linear operator T star is the adjoint or operator, or just the adjoint of T. Okay. So to every T, we can associate T star like this, satisfying this formula for all X and Y. Okay. A remark here. So again, about the importance of finite dimensionality here. So as the theorem says, every linear operator on a finite dimensional inner product space has an adjoint. So adjoint may not exist if the dimension of V is infinite. Okay. And if you're curious to see an example of this, this is exercise, I think, 6.3.24 in the book. Okay. So it's possible that for some operators, there are no adjoints on infinite dimensional spaces. However, on finite dimensional inner product spaces, adjoints always exist. And in fact, we have an easy way to calculate the matrix representing the adjoint. It corresponds to, well, as usual, we have this relation to matrices, right? So it corresponds to the adjoint of a matrix representing T. So this is theorem 610, which tells us how to, what happens at the level of the matrices representing these linear operators. So let V be an inner product space. And the dimension of V is finite, okay? Let beta be an orthonormal basis for V. And here it's important that we take an orthonormal basis as opposed to just arbitrary basis for this formula to hold that I'm about to write. So then if T is some linear operator on V, then if we want to understand calculate the matrix representing the adjoint with respect to B, we look at the matrix representing T with respect to beta. Sorry, I said B beta. And we take the adjoint of that matrix. Okay, so we just remember we defined the adjoint of a matrix earlier. Right? Okay, so this is easy. You just transpose and take complex conjugates. So the matrix is actually easy to understand for the adjoint, but then it has this nice property stated in the theorem earlier. And the corollary of this, the last thing we say, I guess we need from this review, we have a corollary which says that if A is an n by n matrix over the field of scalars F, then if we look at the linear operator LA star corresponding to multiplication by A star, then this is going to be the adjoint of the linear operator LA corresponding to multiplication by A. Okay, so this is of course an immediate corollary of the theorem, because remember LA is represented by the matrix A, so we get this. Okay. All right, yeah. So these are the adjoint operators. So next time we will discuss the situation when, well, we'll discuss how the operator and its adjoint are connected to each other, and how in some nice situations we have some strong connection between the two. And this will lead us to certain special kinds of operators, the so-called normal and self-adjoint operators. So if you want to look ahead, you can check those out. Okay, but otherwise I'm going to stop here. So all right, yeah, thanks everyone for your attention.